Hi, this is Noson Yanofsky. We're doing analysis of algorithms, and we're in the middle of dynamical programming. We're up to sections 15.4. We're going to talk about longest common subsequence. Let me tell you what that's about. You're given two texts, x and y, and you want to find a subsequence that's in both of them, okay? That's the largest amount. So look at this. I've underlined what's in the subsequence, C, B, A, D, A, D, C, and C, B, A, D, D, B, C. I gotta lift out that B, C. I'm sorry, I left this out. C, B, A, D. No, look this. That's that. B, C. A, D, D, B, C. Okay, so they don't have to be connected. This is different than the maximal subarray, where the subarray had to be connected. Okay, here is two subsequences that have it. So the longest common subsequence, the answer to this question, this is the given input, the answer would be this. Okay, and this has uses all over, including DNA research, which is very important, and stuff like this. So I'm going to show you how to do this, and you'll see. First we have to do with a little bit of theory, and then I promise you'll understand the theory at the end. And it's a theorem on page 392. It says as follows: let x1 through xm, let x be from x1 through xm, y be from y1 to yn, be sequences. Then z is the longest common subsequence. So z goes from 1 to k. So again, these are all letters, and we're dealing with them like that. Z has the following three properties. Okay, by the way, is the longest common subsequence. There could be more than one longest common subsequence. But the main point is, if you have two of them, they have to be the same length. They might be different sequences, but they have to be the same length. The longest means it has to be the same length. So there could be more than one. Okay, anyways, Z has the following property. If xm equals yn, now don't change your notes on this, but let's just say we do that. Let's say there's a b over here. Okay, so that means they finished at the end. They finished with the same thing. So if xm is equal to yn, then zk is equal to xm, which is equal to yn. Then the last part of the longest common subsequence is this shared thing. Okay, is the longest common subsequence. Okay, then zk is the last one, so zk would have that extra b. You know what? Let's make that in red because we want to show it's different. So let's for a minute assume that there was a b there. No, red does not work. Green it is. Let's assume that there is a b there. Okay, now they're the same thing. Then watch what happens. Then the last part of zk, the last part of the longest common subsequence would be that b. Hold on. And furthermore, z1 till zk minus 1, that means if you cover this over, this is going to be the longest common subsequence of that. Okay, of the words before the common b. Let's just say that again. So if the end letters are the same, then the end letter is in the longest common subsequence because you can easily add it on. Okay? But what we're saying then is, close this off, the rest of the longest common subsequence is the longest common subsequence of the previous things. Now what I just showed you was how to write a longest common subsequence in terms of previous longest common subsequence. Okay, that's the main point, and that's where the dynamical programming is. The dynamical programming is kind of recursion. It says you want to solve a problem, look at the smaller problems. So you want to find a problem like this, you want to find the longest common subsequence, so okay, the b's are there, and that's going to have the longest common subsequence. So you have to look at the previous longest common subsequence. By the way, the previous longest common subsequence are all going to be, they're the same, okay, and finally we're going to get to something where it's not the same. So this is a D, this is a D, but A and B is not the same. By the way, okay, so that explains this. Hold on, and I promise you, it's a little bit theory, but I promise you at the end you'll understand this because it's Now, what if they're not equal? Like this, B and C are not equal. Then ZK not equaling to BM, oops, they're not equal, so that's gone too. Okay, so then ZK not equaling to XM, so here's ZK, it's not equal to XM, exactly like this, implies Z is the longest common subsequence of X through M minus 1. So watch this. This is the longest common subsequence. C is equal to this. It is not equal to this. Okay? So what are we saying? What we're saying is this is the longest common subsequence, the whole thing, Z is the longest common subsequence of X1 through XM, cover that over, okay, and Y. So this is the longest, so this didn't add anything to the longest common subsequence. Okay, great. Next, if XM is not equal to YN, then CK is not equal to YN, so it's the other way around. I don't want to do this, I don't want to mess up your notes. It's the other way around, and C is the longest common subsequence of the other two. Now, you have to write this down, take it from the book. I used a little different notation from the book, but I'll explain it to you, and then once you see the way I explain it, you'll understand it perfectly. Okay? Okay, great. So, again, the main point is, we're looking to, in order to solve the longest problem, we have to solve the shorter problems first. Okay, great. Okay, so the way we do this is the way we do all dynamical programming is setting up matrices. So we're going to set up matrices, and the matrix we're going to set up is Cij, Ci, comma j. Okay, it's going to be a two-dimensional matrix, and such that Cij is equal to, okay, the length of the longest common subsequence of xi. Okay, let me explain to you what xi is. Hold on. It's better write it like this. x1, x2, x3, xi, n, y1, y2, y3, yj. In other words, the ith first letters of the xi and the y and the j first letters of y. Okay, great. Now we have the following. The following goes as follows. Okay, so now I have to tell you how to fill this in, and you're going to see, you're going to fill in the ij by looking at the previous ones. And so it goes as follows. Cij, okay, is equal to one of three things. 0, Ci minus 1, comma j minus 1 plus 1. Okay, I'll give you the reasons why. And the other thing is the maximum of Ci, comma j minus 1, comma Ci minus 1, comma j. If, okay, so let's do this. If x, if I equals 0, or j equals 0, if x I equals y j, if I comma j greater than 0 and xi is not equal to xj. Okay, great. So that's the formula. I'd like to explain the formula. formula is like this. Okay, this is a part. This is a part of the C matrix, and you might say that this is the ith part, and this is the J. This is I minus. Oh shoot, J minus 1, I minus 1. Okay, so this is part of the C matrix. The idea is as follows. Question: what is the xith letter? What is the yjth letter? Okay, in other words, I'd like to fill this box in. And the idea is as follows. If these letters are the same, I'll explain the 0 in a few minutes. If these letters are the same, that means the end of the word is the same letter. So these two things are the same letter. So what you do is you look at xi minus 1, yj minus 1. You look at this point and you say, look, these two letters are the same. So whatever the longest common subsequence of this is and of this is, well, I got a new one here because these two letters are the same. So in that case, I would look here, okay, I would look here and I would say, whatever the answer is to the longest common subsequence beforehand, go there and add 1 because I'm adding 1 here. Okay, that's the first one of those 3 properties that we had that was a theorem in the book. The second property is, what if they're not the same? What if they're not the same? Okay, well, if they're not the same, then what you have to do is you either look here or you look here. In other words, you see, okay, you see, okay, is this one the same or is this one the same? Okay, and if they're the same, so you take the larger number from here to here. So that's what this says. The maximum of the larger numbers from here to here, I'm sorry, this one or this one, whichever number is larger, that you put in over here. The key point is, if you want to know the ijth position, you have to look at the 3 previous ones for that. And that's the way it works. Okay, so we have to do an example, and we will do an example. We're also going to do the algorithm, but let me just show you how it works. Stop. Okay, so here's a nice example, and this is this C matrix that we're creating. Okay, so the first thing is as follows, is that C, if I or j is equal to 0, so then this C matrix is 0, because what that says is as follows. Let's look at this point. It says, how much of A matches up with nothing of X? Okay, and the answer is 0. How much of from ACB matches up with nothing of this? And the answer is 0, because we're not even starting to read X. And the same thing up here. You can say CDB, how much does it match up with nothing of Y? Well, 0. Okay, so that takes care of that. Okay? And now it goes as follows. Let's go through let's go through the rest. And again, we're building this matrix. We're filling in this matrix. We're filling in this matrix to find out what the largest common subsequence is. But you'll see we're going to look at the earlier thing. Our main goal is as follows. This is our main goal. Because that says, if you look at the complete x and the complete y, what's the longest common subsequence? Okay? Okay, so let's do this. And the answer is as follows. A is not equal to C. So what we have to do, since they're not equal, we have to, remember this? Okay? They're not equal, so what we have to do is look at the larger number from here and here. What's larger? 0 or 0? And the answer is 0. Okay? But we need another piece of information. We have to know, where is this 0 coming from? Is it coming from here or is it coming from there? So we're going to make the following convention, that if it's coming both from the top and the side, if the numbers are the same, then we're going to make a little arrow going up. We're going to think of it as coming from the top. So we're actually giving 2 pieces of information, and we'll see here. Next. A and D are not equal. So question, what's larger? 0 or 0, and the answer is 0. So we're going to, again, they're not larger, one is the same as the other. Fine. A and B, again 0 and up. Now for the kicker. Ready? A and A. What do you do then? Well, you look at the diagonal. When they're matching, what do? You look at the diagonal, that's B, that's this, 0, and add 1 to it. So it's 1, but make sure you add the diagonal. So notice that arrow is going towards, it's pointing towards the diagonal. You'll see why we need that. Okay, finally, A and D is 0. I'm sorry, A is not equal to D, so we have to pick what's larger, this or this, and the answer is 1 is larger, so we pick 1, and we have a little arrow showing that we're doing that. And finally, A and C, they don't match up, and so which is larger? And the answer is 1, this, and it comes from the side. Great. Now let's go to the next one. Okay? And so we're building this, we're going down this matrix one at a time. Okay? Let's go through it. C and C matches up. C and C matches up. And so it's 0 plus 1 is 1. And we put in a diagonal arrow. Okay? C and D does not match up. So what's larger? 0 or 1? And the answer is 1. And then we put in the side arrow because it's coming from there. C and B, we'll do a little of this and then we're going to get bored of it. C and B doesn't match up, so we look at the maximum of 0 and 1, and the answer is 1, and it comes from there. C and A doesn't match up, so we have 2 places where we can get the 1. So again, we're filling in this thing. C and A does not match up, so we look at 1 and 1. What's larger, 1 or 1? And the answer is 1. Okay, and we have this following convention that when they're both 1, when they're both the same number, we take it from the top. You don't have to do that. Okay, C and D is, again, 1, and we take it from the top. C and C, okay, here's where it gets interesting. C and C matches, and so we look at this one, and we get 2, and we put in a diagonal thing. So our arrows are either this way, up, or diagonal, depending on which of those 3 things that we're taking, 3 properties that we're dealing with. Okay, but let's just see what this says. AC matches AC. So if you look at the AC and you look at this whole thing, yes, it will match and it'll be here. Let's just see where we get this. The main point is the diagonals always give you where it matches. Okay, I don't want to do this, but I don't want to do this because we're going to need it later, but A, see this diagonal and this diagonal, those are the 2 things that give you A and C. Let's do one more row and then we're going to get bored of it. The other row is as follows. B and C doesn't match up, so you look at the max, 1 and 0, and the answer is 1 going up. B and D doesn't match, so we look, there's 1 and 1, so we do 1 and up arrow. B and B matches, very good, B and B matches, so we do 1 plus 1, which is 2, and we have a diagonal. Okay, so the diagonals help us move up. Diagonals means the other thing matches. Let's do this. B and A doesn't match, so we do 2 and like that. B and D doesn't match, so we do 2 and like that. B and C doesn't match, so we do 2 and up. Interesting. Okay, because 2 and 2. Great. So ACB and CDBADC, the only thing that matches is AC. So we can actually even see the way it goes, and it goes like this. This goes here, this goes here. So we're following this along. Okay, and we get this 2 comes from AC. This one and this one. Okay, now you don't have to believe me on this because someone from last semester did this as a program. They wrote out the program and they did it, and this is in your packet, and you can see the way it's highlighted. So here's a long thing like this, and here's a long thing like this, and the end is the largest common subsequence is 7, and you can see the 7 as follows. He actually circled it. Here's a diagonal, here's a diagonal, here's a diagonal. Okay, here's a diagonal, here's a diagonal, here's a diagonal. But you can follow the arrows, and it's boldface, and you can see it. So, and again, he did just like I did, our goal in life, and that's our goal. So he starts it off, and then he shows you how to finish. Okay, very nice. Okay, I want to go through the algorithm. I want to write the algorithm, so... Okay, so I'm not going to go through the entire algorithm. The algorithm is on page 394. The first part just sets up the zeros here and the zeros there, sets up what the array is. But then it goes as follows. You're filling in this array exactly the normal way, not diagonally like you did with matrix chain multiplication. For I is equal to 1 to m, for j is equal to 1 to n, if xi is equal to yj, if they are equal, then Cij is equal to Ci minus 1, j minus 1. The diagonal, 1 over, plus 1, because the new ones are equal, okay? And this shows you what the diagonal is. Well, I'm sorry, this shows you the direction you're getting. Bij is one of three things: diagonal arrow, up arrow, or side arrow, so diagonal arrow. Else, if Ci minus 1 comma j, if going up is more than going to the right, in other words, we're looking at the two diagonals, we're seeing which is the max, then Cij is equal to the max. Okay, so it's equal to that, and Bij is up. If Cij, else, if it's not more than it, then it's equal to. By the way, the reason why I said we always follow the convention up is because that little equal sign. We said if it's more than or equal, then we go up. So that's why we do it. But of course, that serves no purpose. We could have done the side one. Okay, if this was not equal, then we would have done this. Else, if they're not, if up is not more than the left, then Cij is equal to the left, and you point to the left. At the end, return the C matrix and the B matrix. There's another matrix. I'm sorry. There's another algorithm called print largest common subsequence. It's a recursive algorithm, and it's very, very nice, and it's worth looking through. It's in the book, and you are responsible for it. It's a beautiful recursive algorithm. Basically, it says every time there's an arrow, follow the arrow, and when you go up diagonally, then print it out. So it's very nice. Okay, how much work is done? You basically have to fill this m by n matrix. Okay, and you do 1 or 2 comparisons for this m by n matrix. Okay, so it's not hard at all. Okay, and you have to look at this other guy. You have to look at the other thing. Great. We're now finished section 15.4. Now we're going to do section 15.5, which is optimal binary subtrees. So optimal binary search trees. And let's start new. Hi, this is Noson Yanofsky, and we're doing dynamical programming. We're up to section 15.5. Let's just remember, we did 2 other things in dynamical programming. We did matrix multiplication, and we did longest common subsequence. Now we're going to do optimal binary search. So I'd like to go through it. I told you in the beginning that the Corman-Lises and Rivest does it, but also I gave you an entire chapter in your booklet from a different book, Sarah Bassey's book, in which they do it, and it's a little bit easier to understand it from this book, so I'd like to do it in this book. Okay, so they start off with an algorithm, but they have a very good motivating example, so I'd like to show you the motivating example. They give you a bunch of words: ring, has, thing, cabbage, of, talk. There's 16 words, and they put it in a nice binary search tree. Has comes before ring, so it's a left child. Of comes after that. Okay, great. Now, let's say you wanted to search for a certain word, like talk. Okay, well, what you have to do to find that word is go ring to thing. You do one comparison with ring. You see, no, it's more than that. You want to find the word talk. Thing, talk. So you have to do 3 comparisons in order to get it. You have to do 3 pieces of work. Great. If you wanted to find the word pig, you'd have to do 1, 2, 3, 4. If you want to find the word and, you have to do 1, 2, 3, 4. If you want to find the word thing, you have to do 1, 2. If you want to find the word ring, you have to do 1 comparison. So sometimes you have to do one comparison, sometimes you have to do two, sometimes three, and sometimes four. There's only 16 words here. You don't have to ever go beyond four. Now again, this is a play imaginative dictionary. Most dictionaries have thousands of words, giant trees going down for whatever. Okay, great. Let's just go through. They're not finished the input because notice some of these words show up more often than other words. So in the English language, the word walrus doesn't show up a lot. Okay? As opposed to that, the word the and and show up very often. Okay? The word cabbage doesn't show up a lot. Okay? So we have this problem. Some words show up a lot and some words don't. Great. So what we're going to do now is we're going to calculate how much work is done on average. Now, let me just explain to you how this is done. I want to calculate the average age of the people in the class. Well, one way of doing it is, sorry, you're a little bit too close, getting on my nerves. You want to calculate the average. One way of calculating the average age of everyone in class is go through every single person, add up their ages, okay, and then divide by that. Okay, there's another way. The other way is as follows. Take all the 18-year-olds, okay? Question, if I randomly choose a person in the class, what's the chances of them being an 18-year-old? Okay, take that probability, multiply it by 18. Then take the probability of choosing a 19-year-old, multiply that by 19. Then find the probability of being a 20-year-old, multiply that by 20, etc., etc. Okay, so you're multiplying the probability of somebody being a certain age times that age. If you add up all those probabilities times the age, you get the average age. This is the same thing we're going to do now. We want to find out the average amount of work. Okay, and the way we do that is we add up what the probability of finding such a word times how much work is done, CI. Okay, that's what we're going to do. Okay, and the book does it very nicely. We made a nice chart. And in this chart you have the words and, okay, and it gives you the probabilities that these words show up. Okay, very good. They find the probabilities in different ways. It doesn't matter. The chances total is 1, 1, 1. Great. Now, once you have the probabilities, look what they do in table 6.2. They have the words, the probability of the words, and for each one of the words, how much work it takes to get to them. In other words, how far down the tree they are. Now let's go through it. The word and is 4 because it's down there. 1, 2, 3, 4. The word said is 4 because it's over here, down there. As opposed to that, the word wall, or the word time is 2. Where's time? Let's forget about time. I guess that's the thing. Walrus is 3. 1, 2, 3. Okay, I have no idea where the word time is. That's a mistake over there. Look at that. Okay, the word the is 4, etc. Okay, great. So they get the probability times the amount of work, get all that, and what the total number they get after the end is 3.25. So, 3.25. Let me just explain to you why it's 3.25. Because if you look, you have 8 out of the 16 words are 4 operations away. The rest are less. But if you notice, the word and the show up very often, and they're more than 3. So again, 8 of the words are 4 operations away, so that would make it 4. 8 of the words are 3 or less, so you would think that would be less. But because very popular words like and the show up in 4, as opposed to that, very unpopular words like cabbage and walrus show up at 3, which is less, so you get something like 3.25. Very good. Question, can we do better? can we make a better tree than this tree? This seems like a nice tree. We always said we want short, stout trees. That's a short, stout tree. We always love short, stout trees. Can't get any shorter than that. You can't have 16 words in a binary search tree that's shorter than that. And yet, can we do better? Okay. The answer is yes, we can. We can build a better tree. We can make a better tree, but in order to do that, we have to solve little problems first. Okay, so let's deal with this little problem. You have, instead of 16 words, let's deal with 2 words, cabbage and cum. Okay? Cabbage shows up 0.025 times, cum shows up 0.05 times. Okay? And the average amount of work here, so cabbage, CA, comes before CO, and so you're going to have cabbage and then cum, or you can have cum and then cabbage. The average amount of work here is, this is the probability of cabbage times 1 operation, plus the probability of cum, which is 2 operations. You multiply that out, you get 0.125. As opposed to that, cum is 1 operation, it's 0.05, 1 operation. Cabbage is this. Okay, question, which one's better? The answer is this. This one has the average amount of work 0.1. This one has the average amount of work 0.125. Great. And it makes sense. Why? Because the word cum shows up more often than the word cabbage. So you might as well have it on top of your tree as opposed to the bottom of your tree. Okay, and that's the way it does. Okay, so that makes sense. Great. Now let's add in a third word. And the third word is and. I should add it over here because we're doing this in alphabetical order. The word and let me just tell you that the word and shows up 0.15. 0.15. So the word and is very popular compared to the other two. The word and shows up very popular. Okay, great. Now what I'd like to do is I'd like to figure out the proper binary subtree for these 3 words, given these probabilities. Okay, so I want you to sit, notice and comes before cabbage, which comes before cum. I'd like you to sit down, shut the WhatsApp, the YouTube, and make me binary trees with these things. Okay, and then try to see for yourself which one it is. Okay, so try to do that. Okay, well, for 3 words, here's 5 possible trees. 1, 2, 3, 4, 5. Let's just go through them. You can have and then cabbage comes after and then cum comes after that. You can have cabbage, which is the middle word. On the left you have and, on the right you have cum. You can have cum, which is the last word, and to the left of that you have cabbage, and to the left of that you have and. And here you can have and then cum, and then cabbage is to the left of that. Or you can have cum, and then and cabbage is to the more of that. Okay, let's just go through. You can calculate each one of them. And is 0.15 times 1 operation. Cabbage is 0.25 times 2 operations to get to there. And cum is 0.05 times 3 operations, 1, 2, 3, and you get 0.35. As opposed to that, cabbage here is 1 operation. And you have these 2 are 2 operations, 0.5 times 2 operations, 0.05 times 2 operations. That gives you an average amount of work of 0.425. Okay? If you look at it, this is the worst case, and if you think about it, why? Because the most popular word is and you're putting it all the way down at the bottom, 3 operations. As opposed to that, the least, well, cabbage is pretty bad, and cum, which is all the way up. Okay? So, of them all, if you look through all these numbers, 0.5, 0.35, 0.425, 0.65, 0.325, this is the best. Okay? This is the absolute best, and the reason is because the most popular words come on top. The second most popular word is the second one, and the third. You might think, hey, maybe you should do this one because this one at worst can have 2 operations. But no. This one, even though there's a 3rd operation, because you brought the most popular word up, then you have the best. Great. Question. What about 4 words? Let's say I had the word zebra in here. Okay? Well, it might be an idea to sit down and calculate exactly how many trees you can get with 4 words. Let's just do some of them. Zebra can only come over here. Zebra can only come over there. Zebra can come over there. Zebra can come over there. Zebra can only come to the right of come. Okay? But if you do it carefully, okay, you could also have something like this. Zebra. Okay? And here you have come, and then here you can have the whole thing. Okay? If you do it carefully, you will see, you should try it, how many trees, guess how many trees you can possibly have with 4 words. Okay? And the answer is 14. Okay, let's just see this. Okay? For 2 words, there are 2 possibilities. This possibility and that possibility. For 3 words, so this is with 2. I'm sorry, yeah, for 2 words. Sorry, for 2? Right. For 3 words, we had 5 possibilities. So for 2 words, there were 2 possibilities. For 3 words, there are 5 possibilities. For 4 words, there were 14 possibilities. Did we see these numbers before? And the answer is yes. Okay. These are what we talked about. Catalan numbers. Catalan numbers. Okay. We gave the formula for them last time, but it's not important because we're not going to deal with it. However, if you look at the formula for the Catalan numbers, it's 2 to the n, choose n over n plus 1. And here we might be n or n minus 1 words, I don't know exactly, whatever, but these show up. And the main point is that this is exponential. Okay? The amount of possible scenarios is exponential. So you can't say to me, oh, you want your best binary search tree? Search through all possible binary search trees and see which one's your best, because the amount of binary search trees is exponential. Okay? So maybe there's a better way of doing it, and the answer is there most definitely is, and that's what dynamical programming is all about. Okay, so we have to go through how are we going to solve this. Okay, and the idea is as follows. You have a bunch of words, which we'll call keys. Okay, you have a bunch of words, and you want to know how to set them up. Now, let's say they're in alphabetical order. K1 is before K2, which is before K3, etc., etc. So here's one possibility. K1 over here, that's the first one, and over here, you're going to have K2 to Kn. In other words, make K1 your root, and this whole tree should have these things. Great. Here's another possibility. K2 should be your root, K1 should be a left child, and here you should have a whole tree of K3 through Kn. Okay, that's another possibility. What's a third possibility? You could have K3 over here, and here you can have a small tree with K1 and K2, and here you're going to have a giant tree with K4 through Kn. By the way, what is the best way of organizing your tree with K1 and K2? Answer, we already determined that. There's where the dynamical programming comes in. You already saw how to set up K1 and K2, so we're going to know how to do it. What's the best way of organizing a tree with K3 through Kn? You're going to already see that. You're going to already see what the best way of doing it. Just like we saw with the matrix multiplication, when we associate, when we parenthesize a group, we already saw that smaller group. We saw what the best way of doing it. Same thing here. Well, K1, there's only one way of organizing one thing. K2 through Kn, how are you going to see it? Well, you already know the best way of doing it. Okay, let's just go on with this. What's this? K4 here, and this is going to have a tree with K1 through K3, and this is going to have a tree with K, I don't know why I'm making that bigger, but it doesn't matter. K4, so this is going to be K5 through Kn. Okay. Let's go to the end. What's going to be the end? The end is going to be something like this. Kn minus 1. You're going to have Kn over here, and you're going to have a giant tree here with K1 through Kn minus 2. And finally, the last possibility, and by the way, how do you organize this? We're going to store that information beforehand and see how we're going to organize it. And Kn over here, and then over here you're going to have a giant tree with K1 through Kn minus 1. Okay, so here's what you're possibly going to look at. And you're going to have to try all these possibilities. This is very, very similar to what I did with the matrix multiplication when I did this. Remember this? I had parentheses like this, or parentheses like this, or parentheses like this, or parentheses like this, or parentheses like this, dot, dot, dot. Okay? That's the same exact diagram. How should we parenthesize this with these things? Great. Okay? So, it's a good question. Let's get to the answer. Okay, how do we do this? And the way we do this is, as we do in all dynamical programming, we're going to set up a matrix. And the matrix is going to be called M. Okay, and we're going to see as follows. We're going to set up Mij. Okay, Mij asks the following question. What is the least AN, where AN is the average amount of work, for a tree that has the keywords Ki till Kj. In other words, if I start at Ki and I go till Kj, what is the best possible tree I have that? Okay, that's what we're going to do. Okay, we already saw that M1, 2, 3. Let's just remember, 2 is the cabbage word, 3 is the com word. Okay, this is equal to 0.1 because we needed 0.1 operations to do those two words. Okay, and we also saw that M1, 3, that's from the word and to the word cabbage, to the word com. Okay, that's 0.325. Okay, so we already calculated that, but we're going to do it in a more general setting. Okay, and what's our goal in life? Our goal is to calculate M1, N. You're given N words and you want to do it. Now I just want to tell you why this is important. Every one of your cell phones has a binary search tree. When you type in text, when you're texting and it gives you the closest word nearby, auto texting or whatever the hell that's called, okay, what's going on there is while you're typing in, you're going down a binary search tree. Okay, so every one of your cell phones has a binary search tree in it. Every dictionary online has a binary search tree. You want to get to the words quicker. Now, your typical phone has about 100,000. Your typical phone has about 100,000 words in it, or maybe 200,000 words in it, etc., etc. And so you want to try all possible binary search trees and put them correctly. Well, that's going to take you n plus 1. Try that. Plug in n is equal to 100,000. See what you get. You're going to blow your computer away. Okay? There's no way your computer is going to give you that possible answer. So you're not going to be able to do that. That's an exponential problem. You're not going to be able to do it. You better do it with dynamical programming and get the best possible results. Okay? Great. So how do we fill in this matrix? And the answer is as follows. Mij is equal to the smallest, because we're looking for the best possible thing, okay, of the same thing as before. I less than or equal to k less than, one of them is probably not equal to j, okay, and it goes as follows. M I comma k minus 1 plus something. I want to leave that blank for a second. Plus, okay, so that's one part. You'll understand in a second. M k plus 1 to j plus something, leave that alone, plus pk, and I'll explain to you what that is in a second. Okay, so that's this, okay, plus pk, that's good. Okay, and let me just show you what we're doing. You want to know what's the best way of organizing the words from I to j, okay? You're going to look at all possibilities with k. So basically, you're going to look at the keyword with a little k over there. You're going to have over here from ki to k little k plus minus 1. And on this side, you're going to have k, capital K, k plus 1, all the way till kn. Okay. Very good. Okay. So you're going to try all the possible roots of this. Okay. Okay. And you can totally describe this tree by just telling it who's the root. Once you know who the root is, you know that these guys are on the right, and these guys are on the left, and these guys are on the right. And you have the information about how to arrange this tree well, and you have the information about how to arrange this tree well. Okay? You probably don't want equals here, and you don't want equals here. Okay, great. What about these terms? I don't even want to write it up. Basically, they're as follows. Look, I can tell you how much work is done here, but how much work is done when this tree is over here? Okay? In other words, there's some node over here that takes, if you just look at this tree in isolation, that's going to take one operation. But now, it's going to take two operations in this tree, if you're looking at this tree, because it's going to have to look at this thing and then this thing, so that's two. Same thing here. This might take 15 operations. But now, when I look at it from here, there's one more. So I have to add extra things. So the average amount of work for these guys in this giant tree, I have to add some things. And the things I'm adding are the probabilities. Same thing here. If you look at this tree by itself, this, to get to this word, is one operation. But now it's two operations. So you have to add certain things here. And the same thing, P of k, because what's this? Because that's the probability that the kth word is done. So that's one word there. So again, this deals with the left side of the tree, this deals with the right side of the tree, and this deals with the root of the tree. If you want, I could do P of k times one operation, because that's that. Okay, now, the book fixes this formula, and they make a nice, beautiful algorithm that does this. And the algorithm looks something like that. I'm sorry, the matrix that you're looking for looks something like this. P1, P2, P3, P4, P5, Pn. Okay, all these guys are 0, not interesting. Okay, and what you do is as follows. By the way, this says, look, if I only have one word, so it's going to have K1, how much work is done? Answer, K1 times P1, that's one piece of work. Okay, okay, so this is my stupid tree. It just has one thing in it. Okay, it has one node. It takes one operation to get to it. And what's the chances of that one operation happening? P1. Okay, if I'm talking, let's just talk about this stupid tree. It's going to be K2. It how much work is that? P2. So that deals with the diagonal. Okay? And then you build up. Okay? Et cetera, et cetera. Our goal in life is the 1n position, because that's going to give you how much average work is done from, if you have all the words from 1 to n. That's our goal in life. Okay? Okay, great. Now, I have to tell you something. Okay, let's just go through this. The book gives you the formula, explains it. This is the Bassi book. Explains to you the formula. Then it gives you the algorithm. Optimal binary search. You enter an array of probabilities and an integer, and they give you this beautiful, beautiful algorithm. And there it shows you, and it shows you how to fill in this tree. And how do you fill it in? You put down the zeros over here, you put down the probabilities over here, and then you put down the things over here. And you slowly fill this tree up till you get to your goal. Okay? You're doing the smaller answers before you get the bigger answers. Okay. And then it finishes, it talks about how much work is done in order to solve this, and basically it's the same thing as before. It's about n to the third. You have n squared, this is an n by n matrix, n squared over 2 boxes to fill in, and for each one of them you have to do a minimization, so it's about n to the third, a little bit less than n to the third, because you don't have to do this, you have to do n operations here, you don't have to do n operations here, here you do much less. Okay, very good. One thing, okay, our book, Corman, Lysis, and Rivest, does something similar, but they get much more complicated, okay? And the more complicated is from the following fact. They say, look, I want to know how much work is done on average, but I want to know what happens if I don't if I look for words that are not in my tree. So that makes the whole thing a little bit more complicated. They have dummy variables. So it goes as follows. You have K1, you have, let's make this K3, you have K2, you have K4, okay, you have K1, you have K5 over here. Let's make this 5, make this 6, make this 4, something like that. So that's usual, that's a typical binary tree. But in Corman, Lysis, and Rivest, they say, okay, but let's say D1, D2, D3, D4, etc., etc. They put in other words. Let's say you're searching for other words. How much work do you have to do in order to see that the other words are not found? Okay, so they're a little bit more exact. Corman, Lysis, and Rivest is a little bit more exact in getting the right results, but they make their algorithm a lot more complicated. Forget Corman, Lysis, and Rivest's algorithm for the optimal binary search tree. You have the booklet. Look through the booklet and get that. Okay, so that's what I want to tell you. Great. Now let's look at it and let's see. There's something missing here, and I'd like to show you what's missing. The book gives you a problem. We start off giving you a problem of these search. They show you the probabilities. They show you how much work is done on average, 3.25, very nice. They show you how to possibly solve the algorithm. Okay, very nice. We drew this picture. They show you the matrix. They show you how to fill the matrix with which formula. They even give you the algorithm of how to slowly fill the matrix. Very nice. What's missing here? What's missing is, look, you had a good problem like this. I'd like to know your results for it. In other words, if we plug this into your algorithm, what's the proper results? The book doesn't give it. Okay, and that's a damn shame. Okay, that's a damn shame. So, thank God you have a beloved teacher who takes care of you and is always thinking of you. I actually wrote out the algorithm. I actually sat down at the algorithm and I wrote out the algorithm. Okay, and it's after the chapter that we did, and here it is. Okay, see, here's that longest common subsequent thing. Here's the algorithm. I wrote out the algorithm for the inputs that they gave for those words, okay? And I did exactly the algorithm. The algorithm is in a programming language, whatever, it doesn't matter. You can read it yourself. And I print the results. And print also, you want to print off at each time who is the root. And I'll show you what. Okay, turn the page. There's more the root matrix. Okay, and here's the results of that algorithm. I circled certain letters, and I want to show you what the letters are. Okay, this is what's called the root matrix. Let's turn the page over for a second. This is the final results, okay, of how much work is done. And, okay, so we'll come back to that in a second. It says as follows. Let's erase this. Follow this. You're the root matrix. If you want to do all the words from 1 to 15, the root should be 6. 6, great. Now, over here I'm going to have a tree of all the elements from 1 to 5. Question, who should be my root of all the elements from 1 to 5? So you look at the root matrix. From 1 to 5, the root is 1. Great. Okay. This does not have any left children because there's nobody before 1, but there is people before. There are numbers from 2 to 6. I'm sorry, 2 to 5. So this is going to have a tree from 2 to 5. Question, who's the root from 2 to 5? So you go 2 to 5, the root is 3. Great. Question, from 1 to, okay, this is going to have a left child. It's only going to have one thing in the left child, 2. I don't even have to look it up, but I may as well. From 2 to 2 is 2. There we have it. Okay, great. And this has a right child. It's going to have everything from 4 to 5, not 6, 4 to 5. So if I look up 4 to 5, I get 5 as my root. Okay. And 4 is going to be his left child. Same thing on this side. Here I'm going from 6 to 15. This tree over here is going to be from 6 to 15. Who is the root from 6 to 15? So I go from 6. Ooh. I'm sorry, I made a mistake. 6 is over here. It's from 7 to 15. Who is the root from 7 to 15? Answer 11. Okay. You don't have to do this anymore because I actually worked this all out with the words 6 to 1 to 3 to 2 to 5 to 4. Okay, 11. Here you're going to have the root whatever, and I added in the words over here. And lo and behold, look at this. The word of, the, and the are on top. The word pig, walrus, and has are words that are on the bottom. Okay. Now, this is not a short, stout tree. We spend our whole time talking about how we like trees that are short and stout. Now we've changed our mind. Yes, we do like trees that are short and stout, but we also like important things to be on top, less important things to be on the bottom. We're going to see this also in chapter 16 again. We like important things to be on top, less important things to be on the bottom. Okay, so this tree is not as pretty as Sarah Bassey's tree because it's a little bit cockeyed. Okay, and there are some things there you only had to do 4 operations at most. Here you have to do 1, 2, 3, 4, 5 operations. That's bad. 1, 2, 3, 4, 5 operations. So it's not as short as Sarah Bassey's original tree, but this tree has less work because we have more popular words like of, and the on top and less popular words on the bottom. So it really works. It's a beautiful thing. By the way, here's the root matrix. You can see the root matrix by just doing this. This is going to be your root 6, then you're going to have the 11, then you're going to have the 1 on this side, 3, 5, 11, 9, 10. You're going to have this on this side. You really have to study this to understand how it works, and you have to study the algorithm. And you have to study the algorithm. Great! So I've given you the better binary search tree. The book didn't do it, but I did it for you. You can send your donations, but it doesn't answer the question, how much work is done with your better binary search tree than was done before? And the answer is, here is the matrix with all the work. Notice, all these are zeros. Down the diagonal you have the probabilities. The 1, 2 position, the 2, 3 position is 0.1, we saw that. The 1, 3 position is 0.33. They're rounding up or they're rounding down, I'm not sure. Okay, and if you look totally, how much work is done on average? 2.92. Okay, as opposed to that, when we started, and you look in Sarah Bassey's book, you'll see that her average amount of work is 3.25. Okay, now that's for 15 words. It's not a big difference between 3.25 and 2.95. But if I had 100,000 words, you better make sure that you do it as an optimal binary search tree with the more popular words up on top of the tree and the less popular words on the bottom. Okay, so that takes care of that. Okay, and again, you're not responsible for the algorithm that's done in Corman, Weiss, and Rivest because they get a little bit more complicated, but you are responsible for Sarah Bassey's algorithm. Okay, so that is the end of chapter 15. And that's the end of dynamical programming. You will see dynamical programming comes up a lot. Not every day, but it comes up a lot. And we like dynamical programming because it's recursion, but it's manageable recursion. It's not doing self-calling. It's filling in a matrix with information. So you take your data, you fill in the information, you get to the end of the thing. Okay, sounds good. Have a great day.